All right, let's get started. Hi, everyone. Thank you for joining my talk on Year of Fuzzing with Zen. My name is Tamas Lengyel. I'm a senior security researcher at Intel, and I'm a maintainer of Zen's introspection subsystem as well as libVMI. And my background is mainly in malware research and black box binary analysis. So there's a bunch of things I want to talk to you guys about in this presentation, primarily what's new since Zen's 4.14, and then take a look at fuzzing various targets that we've done in the last year. At the end, I will talk about taint analysis and release a new tool, and then wrap up with future directions of where this project is heading. So the major feature that got released in Zen 4.15 is VM trace. This is the ability to use Intel processor trace from DOM0 monitoring the entire execution of a guest VM, including both user space and the kernel, which is just a awesome way of doing introspection. And this is a unique feature for Zen. No other mainline hypervisor supports this. So it's been awesome to get this upstream. And we have been using this feature internally since the fall of 2020 in a bunch of different fuzzing setups. We've completed billions of fuzz cycles with it. And what it effectively gets us is a speed up in fuzzing. We can get about 10,000 times better speed while fuzzing because collecting coverage information using the processor itself is way faster than doing it manually using disassembly, breakpointing, and single stepping. So this is a major upgrade in the fuzzing process on Zen. In terms of the fuzzer itself, there has been a bunch of new additions as well. Top of the line would be the ability to use breakpoints as the harness. So when you're fuzzing, you want to put a harness around the code you're fuzzing so that you can revert the state of a VM over and over. And the default one is to use a CPU ID, which you need to compile into your target. If you can't compile your target, though, then you can still use breakpoints. So effectively, this allows us to fuzz binaries that you can't recompile. If you can recompile your target with the CPU ID harness, then we've been working on better automation. So the harness can actually be extended to stuff extra information into general purpose registers while the CPU ID instruction is executing. So for example, if you want to stuff a virtual address and the size of your buffer that you want to fuzz, you can do that automatically with the CPU ID harness so that you can do better automation. Another feature that was added is to be able to detect double fetches during fuzzing, which is a type of bugs that usually happen on DMA buffers where you have time of check to time of use errors. When the kernel would, for example, fetch the same memory from DMA twice in a row, that value can change in between those two fetches, and that could yield bugs in the kernel that are very hard to detect because even source code analysis usually don't show those types of bugs. So now we have the ability to do that by simply removing the EP3 permissions and watch as the fetches happen to target memory pages. The other feature that we worked on is to be able to utilize in-guest kernel features such as the kernel address sanitizer and the undefined behavior sanitizer so that we have even better bug detection capabilities. And effectively what we can do is compile those systems into the kernel that we will be fuzzing. And when any of those bug detection system trip within the guest, we can actually get the report out by dumping the dmessage buffer directly from memory from DOM0, which effectively gets us very detailed information about what bug was encountered. I will actually show a demo of this shortly. So we've been fuzzing Linux, obviously, for the last year. We have been focusing on MMIO and DMA input points of the various kernel modules, mainly ones that Intel maintains. And the motivation for this was basically that the threat model for the kernel is changing. A lot of the devices that the kernel modules written for these devices were written with the assumption that these devices are wired into your system and can be trusted. Whereas now with Thunderbolt, a lot of these devices can be actually plug and play. So you can actually walk up to a system, plug something in, and it will pop up as a PCI device. And obviously, if that kernel module was built with the assumption that that device is always trusted, well, that's no longer the case. So we started fuzzing a bunch of these drivers to see what happens if the device is no longer trusted. And to no surprise, we found a bunch of bugs. So far, we found 9 null-pointer dereferences, 3 array index out of bounds, infinite loops in interrupt context, and we could even trick the kernel into trying to access user space memory. Obviously, none of these are good, but the good news is that with this fuzzer, we were actually being able to find them and fix them, and these are all now fixed upstream in Linux. So let's take a look at the actual demo of a real bug that we found just a couple months ago in the IGB kernel module in Linux. So IGB is a gigabit network driver that receives packets from the wire. And one of the information that this device places on a DMA buffer is called the RX description buffer, which describes some metadata about the packet that was just received on the wire. So this is not the packet itself. This is just information about the packet that the device gives the kernel. So what you see here is the actual interrupt handler that gets fired when a packet was received. And what we will be doing is actually fuzzing that RX description buffer. Here at the bottom, you see the harness start. This is where we will start the fuzzer. And we are passing the virtual address of this RX description pointer and the size of that buffer directly to the fuzzer. And we will stop when this loop loops around. And there's also a harness stop if anything breaks out of this loop. But all the code that comes after is what we will be fuzzing. So let's take a look at how this actually works in practice. I will be sharing a video, external video, hopefully. This loads for all of you. And you can actually see the text here. Effectively, what we will be doing is taking a real PCI device, IGB device, and passing that through to a VM using PCI pass-through. And we will boot up that kernel that actually has this kernel module with the harness compiled into it. So I'm booting with a couple options set here just to make debugging easier, such as KSLR disabled and page table isolation disabled, just to make it easier to debug when something is found. The VM is booting. We'll start KFX to catch when that CPU ID executes with that magic mark, which was 133715000. And we'll pipe the output of that into a log file. So now it's waiting for that CPU ID. It already caught one. We can take a look at what's in the log. So as you see, the target buffer and the size was transferred via that CPU ID instruction. So we have exactly the address of where that buffer is now sitting, and that VM is actually paused in that interrupt handler right at that CPU ID harness start point. So I can actually read that RX description buffer out from the VM's memory using RWMem. That's a small utility that comes with the kernel fuzzer repository. And that's pretty much all we need. We can actually start fuzzing that interrupt handler using AFL. So what you see here is I'm specifying to AFL the input folder where that seed is that it will start mutating from, specify the address that we want to fuzz, and what the size of that buffer is, and that we will be using PTCOV, processor trace coverage. Now AFL is starting up. And it doesn't really take too long before a bug is found. So we can actually break out from AFL, let it keep running in the background. So you actually see that one of the VM forks is still running. So that one is repeatedly executing the interrupt handler with various inputs right now. But in the meanwhile, we can create VM forks in the background as well and do other types of debugging as we need to. So for example, one of the first things we can do is just take a look at the actual buffer that was found by AFL to cause some type of issue. So you see that the buffer was mutated quite a bit compared to the seed. So now we want to figure out what is actually happening here, right? So the first thing would be to re-execute KFX without AFL. And for figuring out what sync point was tripped, we will simply take that output that was found by AFL to cause a crash and feed that into a new VM fork and monitor which sync point was triggered during the execution. For that, we will just specify that we don't want any covered information, but we want verbose output using debug mode. And what we see is that Kazan was actually tripped. So now we know that this input will create a Kazan report. So we want to actually re-execute now sync the end report function, which is the function that gets called when Kazan actually finished printing to the dmessage buffer. And we can actually keep that VM fork alive just enough to carve the dmessage buffer out from the VM's memory directly into a file. and take a look at what the Kazan report actually says happened. So I'm just going to go at the very end of the dmessage buffer. So we see here is the full Kazan report with that buffer that AFL found. And we see that there is a null pointer dereference in a mem copy from a function called GRO pull from frag0, which is actually deeply embedded in the Linux kernel core. So it's actually not a location within IGB itself. But we want to figure out a little bit more of like, okay, what actually happened here. So what we can actually do is with VM forks is do repeated executions, right? That's what the fuzzer is doing, repeated executions. We can actually do that manually as well. And instead of letting the code run full speed, we actually have the ability to single step the entire VM fork instruction by instruction, so that we can actually take a look at the full execution of what that interrupt handler would be doing using this tool called stepper. So this is actually just using the monitor trap flag, and every instruction will be trapping to the hypervisor, and we can log every instruction. We want to stop when the instruction pointer reaches Kazan report, right? So that's the last part we want to stop, and we can actually take a look at the full interrupt handler code as is executing instruction pointer disassembly, which is pretty good. But we can actually take this output and get a little bit more meaningful information simply by decoding the instruction pointers using the kernel's debug symbols. So we can actually pipe the instruction pointer through address to line, and that will effectively get us the exact lines in the source code that we're executing. And we can actually go through step by step of what lines of code executed in the kernel that reached the Kazan report at the end. So if I go down to the bottom, what we'll see is that that's where the mem copy is and the GRO pull from frag function. So we know that this is the end of the execution, but obviously we have the full log from the start to the end. So this is something that's useful to trace the execution. But what's even more useful is that we can actually compare this execution that we know will land in Kazan. We can compare that execution to the baseline execution with the seed that would have normally executed, right? We know that that didn't cause any type of issue. So we can actually compare those logs. So now what I want to do is check what is the last instruction when the normal execution happens, right? So we see that this is the CPU ID leaf 1337, which is the end harness executing. So we know that with the seed, there's nothing bad happening. So I will just repeat the execution with stepper all the way up to that address. And then we can actually compare those execution logs, see where things actually got off the rail. So now I have the full single step log. I will translate that using address to line. And now we can actually just diff those two execution logs, and the first thing that will pop up is where those executions start to diverge. That's likely where the bug is. So here we see exactly the line where those execution logs differ, source and the line number. So we can actually just go there, take a look at what the code is doing there. And that's exactly where the bug was. It was confirmed by the maintainer. So what happens here is that if this bit is set in the RX description buffer, this function here actually modifies that buffer, pulls out a timestamp header, and if that timestamp header wasn't actually there, it just corrupts that packet, and that leads to a null pointer dereference. All right, so let's continue. We can also fuzz windows. We've added some documentation on how to fuzz various things within Windows kernel modules and whatnot. It requires if you want to use debug breakpoints as your harness, you need to set up a cross VM serial bridge. We added a script to the repository that you can use for it, which is very useful if you want to fuzz closed source portions of Windows. Unfortunately, there is no address sanitizer or undefined behavior sanitizer for the Windows kernel, so still requires a little bit more research of what the best points to use as sink for error detection in Windows are. But it's already usable as is, and in the community, people actually started using this for not actually fuzzing Windows kernel, but actually fuzzing user space applications that are closed source by doing effectively reverse system called fuzzing. All right, let's look at another demo here for this one. I want to show you how to actually set up a fuzzing engagement for a closed source kernel module that you don't actually have the ability to recompile. I'm actually going to show you how to use WinDebug for this. On the left, you see one VM running WinDebug attached to this VM on the right, and it's actively debugging that through a serial bridge. And we have this dummy IOCTL kernel module that receives an input from user space and then passes it out on another buffer. And we have a bug embedded here that if the string that is getting passed in from user space starts with deadbeef, it will create a NULL-pointer dereference, and we want to fuzz this function. And the idea is that we don't have anything pre-compiled into this function in the kernel module, but we still want to fuzz it to see if there are any bugs in it. So first I executed it without anything special. So this is what happens. The kernel module gets loaded, this executes and then unloads. The important thing was here to note the first byte of the function that was actually breakpointed, because that byte gets overwritten with the instruction for the software breakpoint int3. So we actually want to be able to replace that with KFX when we actually do the harnessing. So what we do now is, instead of letting WinDebug catch that breakpoint, we want to have KFX catch that breakpoint. So now KFX is running. I go back to the VM, re-execute the loading of that module that will execute this target function. And instead of WinDebug catching that breakpoint, what we will see is actually, if we go back, is KFX got that breakpoint through Zen. So now this VM is sitting at the point we want to start fuzzing, but we still don't know the target address in the memory that we want to start fuzzing, and we also don't have an endpoint specified. So we need to figure those two things out. So through reverse engineering or whatever other means, right now I actually have the source code, so I can just take a look at where the input is coming from. We see that it's coming through this structure called IRP. So I can take a look at the debug symbols of Windows, take a look at the layout of that IRP structure, and find the offset to that pointer that will be pointing to the string in memory that we want to fuzz. So we see that it's at offset 24 within the structure, convert that to hex. And then since we saw that this IRP structure is the second input to this function, we can actually just take a look at the register that Windows uses to pass the second input into a function. So we see that this is the pointer to the IRP structure. We just add the offset we saw before. This is going to be a pointer to the string. So we first read out this pointer. So this is going to be size 8. And once we have that, we can actually read this file that we just read. This is the pointer to the string in memory. This is going to be what we want to fuzz. So just to verify this is actually the string we are targeting, let's read out a little bit from that pointer and see what is there. We see that this is actually a string. So this is the target address that we want to fuzz, right? Now, the only thing that's left is to mark the point where you want to stop fuzzing. So for example, if this is a function entry point, a logical point to stop fuzzing would be wherever this function would return when the return address is popped from the stack. So we can just do the same thing. We can read the return address from the stack, get that address. So we know that this is where the execution would return when this function is finished. So we can manually just patch in a breakpoint. The CC is the instruction for the software breakpoint. We can just patch that in manually. And we are ready to fuzz. We can actually specify whatever we want as the seed, but let's start with capital deadbeef just to be close enough for the fuzzer to find this fast for this demo purposes. But that's all we need to fuzz a closed source kernel driver on Windows. And I will actually catch when KI dispatch exception is triggered within the Windows kernel. And that NULL-pointer is triggered. So AFL found it immediately pretty much because the seed was very close to the actual crashing condition, but we can verify that this actually found the correct crashing condition. And indeed, it actually found that deadbeef triggered a bug within that Windows kernel without the harness being compiled in. All right, we have 10 more minutes, so I will speed up. We can fuzz Zen now. There's actually an ability to boot Zen in PVH guest, and anything that uses just EPT will work for fuzzing, so this is awesome. We actually got this working with Andrew over the winter break. It integrates with XTF, so you can actually build a minimalistic dump0 image, boot Zen as the kernel within a PVH guest, and use the XTF code as dump0. So what you see here is actually this dump0. This would boot as a minimalistic dump0 within that PVH guest on top of Zen within that guest, and you can actually fuzz the domain create hypercall using KFX and use processor trace coverage to find bugs within Zen. So this is verified to work. We actually have a Google Summer of Code student working on this summer to extend the list of hypercalls that we can fuzz with this. So this is going to expand this year in XTF. Another pretty cool thing that we worked on is fuzzing things that are specific to KVM. So right now, nested virtualization is still on the to-do list, so we can't actually fuzz nested hypervisors on top of Zen right now. But what we can do is actually take a snapshot on KVM and port that KVM VM snapshot over to Zen for fuzzing. And this is because when we are fuzzing on Zen, those VM forks have no I/O, no devices, no interrupts, so we don't have to worry about any of those peripherals or anything that KVM normally relies on to actually interact with the VM. For fuzzing, we don't care about any of that. We just want to have target code execute. To actually get the format we need for that snapshot to be loadable on Zen, there's actually this command on QEMU that you can use called dump guest memory that creates an ELF file with the guest memory and the memory map. But it also has a undocumented, as far as I can tell, feature that it actually dumps the VCP registers as well in an ELF node header with the key QEMU. And that pretty much means that this ELF file has everything we need to load it up on Zen, and it just works. So this is pretty awesome. The code for that is already in the GitHub repository alongside the documentation. To actually aid with the capturing of the KVM VM state at the right moment, right? So we would want to have something like the magic CPU ID instruction we use on Zen. So there is a patch to KVM and a patch to QEMU to support that. It's really minimal. You will be able to patch that on top of any version of KVM and QEMU that you need to. But effectively, that allows you to really target the execution within a KVM VM and pause that KVM VM just at the right moment, same way we would do on Zen. So you can port it over to Zen for fuzzing. Right now, I'm using this to fuzz Virtio on Zen, which is kind of a crazy idea, but it actually just works. If you can't patch the CPU ID instruction into your target code on KVM, well, you can actually emulate a function call as well if you need to. So effectively, you can fuzz anything you can boot in a KVM VM on Zen. Again, the documentation for this is added to the repository's wiki as well. Now, what I also wanted to talk to you guys about is this ability to do further binary analysis, which is oftentimes required because you need to figure out where the code is that you want to fuzz. So what we figured is that, especially when we want to catch when things interact with DMA, is we want to know where that code is. So we can actually remove the EPT permission from DMA pages so that those accesses to DMA pages will actually trip to Zen, and we would actually be able to get the instruction pointer to all the locations within the kernel that interact with DMA. Unfortunately, what we found is that oftentimes what happens is that those DMA accesses actually just copy data out to some buffer, and then you don't actually know where the kernel actually interacts with that data. So we wanted to do taint analysis. So on the right, what you see is this tool called VM Taint that will actually use the processor trace feature of Zen to collect the processor trace log, process it, and feed it through a taint engine to actually see where the DMA source data lands in the kernel and where the kernel actually interacts with tainted data. So you have a better idea of where to even look in the kernel to see what portions need fuzzing. So what we can do is record the state. So on the left, you actually see the Zen VM trace command just collected all the logs of the execution of the target code, and we fed it through the taint analysis engine. And you can see each instruction as it's executed and the associated registers that got tainted. So what's important here really is what we use it primarily for is to catch when the instruction pointer becomes tainted. So from that starting point, we can actually see all the different code locations within the kernel that interact with tainted data and depend on tainted data for control flow decisions, which is pretty much means that those are targets for fuzzing. All right, 5 more minutes. So I am going to be wrapping up here. There are a couple things we are looking at where we want to head. Obviously, nested virtualization would be great to get working for fuzzing. But what we are also looking at is snapshotting physical systems. So just the same way we can port KVM VMs over to Zen for fuzzing, we would be actually able to bring whole physical systems over to Zen for fuzzing. The idea is to use Intel DCI, snapshot the full system at various points. And we could use this to fuzz the BIOS, SMM, or any type of code that you have no ability to actually get working within a VM. So we can actually boot those systems up on bare metal, snapshot them, throw them inside a VM, and then start fuzzing it. Another idea is to use the VM forks for SandSifter ring 0 mode. So that would allow us to fuzz the CPU itself, which is also a pretty cool idea. And then obviously we are looking at automation, better figuring out how to automate this process, how to figure out where the target codes are, how to automatically figure out where to stop, and just generally making things a little bit more straightforward to use. So that's my presentation. Thank you for watching. There was a lot of material here, so I'm hoping that you were able to follow. But if you have any questions or comments, please feel free to reach out. The projects are on GitHub and are open source. So SandSifter ring 0 mode. So SandSifter is an open source project that was released a couple of years ago. And it's effectively an idea that you can use page faults to figure out what instructions the CPU supports. So that the idea is that you can actually start generating instructions and figure out what are available on the CPU. And right now, this is limited to ring 3 instructions, but using VM forks, we could use EPT to use the EPT faults as the oracle for instruction sizes. So effectively, we'd be able to figure out what instructions are available on any CPU, see if anything got enabled by accident or anything like that. If there are any other questions, I'm happy to answer. We have 2 more minutes here, so. All right, if there are no other questions, well, I see people typing, so let's wait. All right, thanks, guys.